Okay, this is the second part of our online class. So just to summarize, in section 4.1, we saw that if we have a homogeneous ODE, linear ODE, this is of nth order, then we saw two theorems that guarantees that there exist solutions. There is a fundamental set of solutions. There are n of them. They're all linearly independent, and therefore you can construct the general solution, which yields any other solution that there is for that ODE. So when n is 2, that's the second order homogeneous ODE. So we have the second derivative, first derivative in the function. Then, so the theorem is saying that there are two of them, two solutions that are linearly independent, and any other solution can be written as a linear combination of these two guys. Okay. And then in section 4.2, we saw a little trick called reduction of order, which is basically to from a given reduction of order for second order homogeneous ODEs, like this one here. So it says that if you have one solution, so given y1 a solution, we can find another linear independent solution from the first one, which is y2. And there was a formula for that, and the formula, let me write it here again. It's y1 integral of e minus integral of px dx over y1 squared. Okay. Now the px comes from the homogeneous ODE. So you have to see the px, it will be this one here when this is 1. So we have to do a little transformation here first. So just remember that the ODE, where the ODE looks like this: second derivative plus p of x and plus q of x, y equals to 0. So you have to put the second order ODE here into this form so you can get the p of x. Okay. All right. So maybe I should put that in here. There you go. So this will look better. Okay. Now, in section 4.3, now we're going to do just one little thing on section 4.3, just the first part. So it will be the first 2 pages, the first 3 pages of section 4.3. So I'll write here pages 133 through 135. Okay, and that's all what's going to be on the test. So after the test, we're going to finish section 4.3. Okay, section 4.3 talks about second order homogeneous ODEs. ODEs with constant coefficients. So it basically looks like this. So let me copy that. But instead of functions of x, these guys here will be constants. So I can maybe put the general case here. Yeah, let's say that this is A, okay? This is B, and this is C. A, B, C, constants. When these guys are constants, then it's very easy to solve, and the idea is to realize that one solution well, let me write this way. The solution will have this format. a solution will have this format. It will be something like e raised to mx. Okay, so that's the idea of this this part of section 4.3. So let's see what happens if the solution has this format. Then we can find all three of them. So that's what it's neat. And if we find three linearly independent, then that's it. Those are the solutions. Any other solution will have this format. So if we plug that in there, look what happens. So let's put this solution in here and see what happens. Okay, this would be A. Okay, what is the first derivative of that? It would be m e mx. The second derivative would be m squared e mx. So let's substitute. This will be A. Second derivative is m squared e mx. And then B. And then first derivative m e mx plus c e mx equals to 0. Okay. And then I can factor the exponential out. Mx, this would be a m squared plus bm plus c equals to 0. Now notice that the exponential is never 0. So this is never 0. So this implies that am squared plus bm plus c has to be 0. And now what's neat about this is that we can simply solve this quadratic equation. See, there's no derivatives in there. It's just real numbers here. Solve for m. Okay, so the variable here is m, so it's a simple quadratic equation. And notice that when we solve a quadratic equation, we're going to have two solutions. We could have two solutions, one solution or no solution. If we find two solutions, then that's it. We're going to find m1 and m2, so there are your two solutions. So the second order homogeneous ODEs have two solutions, right? Take a look here. So there are two solutions. Now the problem is when the quadratic equation has only one solution or no solutions. In fact, when it has no solutions, actually this becomes actually easier, because if it has no solutions, then I mean there is solutions if you use imaginary numbers. That gives you two solutions. So we'll see how we tackle that. So we're going to split this into cases. Okay, case number one. There is two. Well, let's put the quadratic equation. am squared plus bm plus c equals to 0 has two solutions. Well, then we can easily find the solutions. That's minus b plus or minus, e squared minus 4ac over 2a. If it has two solutions, that means that the determinant, well, not the determinant, the discriminant, which is this guy here, is positive, right? So that would be the case when this guy here is positive. Anyway, if there's two solutions, then we can have we're going to have m1 and m2. Well, we can say m1. Wait, I'll write the whole thing there. So this would be the second solution. One solution is m1, the other is m2. And then the ODE, the original ODE would be, the solutions for the original ODE would be E m1x, and another solution would be E m2x. Okay. So because the solutions will have this format. And it can be shown that these two solutions here are linearly independent. Okay. So that's actually an exercise. You can check that. Check that y1 and y2 are linearly independent. Okay. So that was easy. Case number 2 is when the quadratic equation has only one solution. Well, in that case, it means that the discriminant of the quadratic formula is 0. If it's 0, then you have a plus and minus, plus 0 or minus 0, so it doesn't give you different solutions, it's the same solution. So you have m1, you just have m to be negative b over 2a. You don't have the plus, well, you do have the plus and minus that, but that it would be 0. So you can only find one solution, so that would be e mx, one solution for the original ODE. But that's not a problem because we know how to find a second solution that is linearly independent from the first one. That's how we use the reduction of order. And so here's section 4.2. If we have one, we can find the other one. So we can simply use this formula here to find a second solution. Okay, so just remember, in this formula here, you have to have the p of x. Okay, let me write the p of x here for you. We have the original ODE here. Oops. So that's the ODE. So I need to get rid of this a here, or make that equals to 1. So I divide both sides by a. So this is your p of x, okay? This is your p of x. All right. So then you can put that in there. And yeah. So found two solutions again, and they're linearly independent. Case number 3, it's an interesting case. That's when this quadratic equation has no real solution, okay? Has no real solution. And that's exactly when the discriminant is negative. So let me pick this one here, and I'll put it right there. So you have, okay, you can pick both. Sorry about this, but trying to save time here. Okay, it has no real solution, but there are two solutions because the discriminant here will be negative. Even though the discriminant is negative, we still have two solutions, but they will be two imaginary or complex solutions. But it has two complex solutions. Then we have to go to imaginary numbers, and then there we can get to solutions. Okay, but how do we use imaginary solutions here? It seems like we are going to an extreme, and then we're gonna see imaginary numbers in there, but that doesn't make sense in the real problems, right? But that's what is neat about this, is because we can go there and then find a solution and then come back and then get you a real solution. So I'll show you how to do that. So this is the idea here. When you have your two solutions, your complex solutions, you're gonna have a part of the solution will be real and a part will be imaginary. So that's why you're gonna see an I there. Okay. So I'll use alpha and beta to represent the real part and the imaginary part. So it turns out that the second solution will be minus bi. So when you solve this quadratic equation and you plug the numbers in there and you simplify, you're going to find a number like this. And then when you simplify this one, you're going to find a number like that. They're conjugates, okay? So that's what is neat about these solutions of quadratic equations. If you find one, then the other complex solution is a conjugate of the first one. Okay, and so there you have it. You have two solutions now. So this would be E m1x, right? Solutions of the ODE. And then the other solution is E m2x. Okay, yeah, it looks strange because we have e to alpha plus beta I x, And then the second solution is E alpha minus beta I x. And that doesn't look nice. Well, there is a little formula you can use. It's called Euler's formula. For complex numbers. I don't know if you studied this in trigonometry or calculus, but anyway, Euler's formula says that if you have e raised to I and some number, let's call it theta, then this can be written as cosine of theta plus I sine of theta. Okay, so we can apply that in here. So if you look at this guy here, okay, well, let's split. So the only part that is troubling here is the bi here, right? The beta I. So let me put I here, beta, and then x, because it will be multiplied by x. So according to this would be cosine of beta x plus I sine beta x. And if we have the negative, so let's put that in here. This will be cosine negative beta x plus I sine beta x. And the cosine is an even function, so it eliminates the negative here. You can actually write this as cosine beta x. And sine is an odd function, so you can pull the negative sign out. Okay. All right, now let's combine that and that. So here we have E alpha plus beta I okay, so this would be E alpha x times E the beta I x, or I beta x, whatever. This would be E alpha x, and then look at this thing here. That's exactly this one here. Cosine beta x plus I sine beta x. Okay, and then the other one, the other solution, which is alpha minus beta ix, then E minus beta ix would be beta alpha x cosine of beta x minus I sine beta x. So that's solution 1. That's the solution 2 of the ODE. Yeah, we still have the I, right? We still have the imaginary number there. But you remember that if we add two solutions, then what we get by adding, we get another solution. So we can simply add these two here. Yeah, we can add and subtract. Let's see what happens here. If we add, that's another solution, okay? Because these two are solutions. If we add, we have another solution. If we add, this would be 2 cosine beta x, and look what happens with the sine, with the I here. It disappears. So we can say that this is our new I'll call, you don't have a notation for that. Let's do it this way. Maybe I should follow the same thing as the book here, the general solution. So it'll be a constant times the first one plus a constant times the second one. So this would be a C1, and then this thing here, okay. Trying to simplify this. Okay, let me put that in here. plus C2, and then the second one. So that's the general solution of the ODE. And then we can pick constants. I'll show you now what's going to happen. We can pick like C1 to be 1 and C2 to be 1. If we do that, look what's going to happen. This would be E alpha plus beta I x plus E alpha plus beta I x, which is adding these two guys here. Right? If we add these two, look what's going to happen with the I sine beta. That's what I said before. It gets eliminated. So this will be simply E alpha x cosine, well, 2, right? 2 times cosine beta x. Now if I pick C1 equals to 1 and C2 equals to negative 1, then I get another solution. It will be minus here. Well, if it's minus, then it will be this first one gets eliminated, and then we have twice the I there. So this would be E 2I alpha x sine beta I. Okay, and then what I'm trying to say here is that here you can see the two solutions right here. We can simply pick these two here, this one and this one, because this is a constant. 2i is also a constant. So remember, if this is a constant, I can divide by 2, and that gives me another solution. And then I can pick this one and divide by 2i, which is a constant, and that gives me another solution. So I could say, I could pick my new y1 to be simply e to alpha x cosine beta x, and then my y2 to be e alpha x sine beta x. Okay. So that is the two solutions that we can use. And if you plug these two solutions in the original ODE, you get it satisfies the ODE, and also they are linearly independent. So in the end, the general solution becomes y equals to e alpha. Just add those two, right? If you add those two, if you make linear combinations, C1 cosine beta x plus C2 sine beta x. Okay, let me summarize this. Case number 1, very easy. We get the two solutions of the ODE. Second one, we get the two solutions because when we solve that quadratic equation, there's only one solution, but we can easily get the second one from the first one. And when it's imaginary solutions, or when it's complex solutions, then here we have the two solutions. Okay. Then you can read examples 1 and 2 on page 135. Yeah, take a look at that, and should be pretty straightforward. Okay, so the idea is they start with this second order homogeneous ODE. It will be constants in front of the y second prime, y prime, and y. So you can call those ABC. So that's easy to remember because it reminds us of the quadratic formula. And then you solve. So because the solution has this format, then you can simply solve am squared plus bm plus c equals to 0. If you solve for m, and then you have these three cases. If you have two m's, then that's the solution. If you have just one m, you can get the second one from here. And if you have complex numbers for your m, then you can use that. Okay? So just remember that here where you get this alpha and beta. It's from your AMs. Okay, your AM will look like this. Your AM1 will be alpha plus beta I. Your AM2, when you solve the quadratic equation, it will be alpha minus beta I. And then from those, we can get the solution this way. All right, so you should be able to do the exercises now. We'll post the exercises pretty soon, and that's all for this lecture.